So quantum physics have been around since the 1950s, 1940s, some early in the 1930s. There are many quantum effects. The quantum computing chip they call a qubit instead of bits. They have qubits, and that plays into the uncertainty. So a bit is a 1 or a 0. A qubit you don't know until you look at it, right? And so the challenge for the quantum
Make a good
computing
aim today on a qubit.
Well, it's 1 or 0.
Oh, okay.
So you don't know whether it's 1 or 0 until you look at it.
Keep
right. And so
going.
if you will, we're back to the chip point. The secret behind the quantum computing chip is you have enough qubits to fit the password, right? So if you only have 1 qubit, it doesn't do you any good. It doesn't do you it does you 1
qubit's good.
1 qubit goodness. So maybe you double your computational speed, right? If you have 2 qubits, now you have 4 times. If you have 3 qubits, now you're 8 times, and so on, right? So to be useful in a practical sense, you need as many qubits as the problem you're trying to solve. Okay. Another aspect of quantum computing is what they call the Hall effect, and they've been using this since they've had transistors in the late 60s. They didn't know what it was. But the whole thing with semiconductors is what they call the Hall effect, and they call these the gates. And so when the current CPU does multiplication or addition, what it's doing is it's forcing the values of the register through logic gates. And the logic gates are on and off, and they do some computation, which is what electroengineering does. To organize the gates, so as the data in the register goes through the logic gates, out comes the problem, right? The solution. Now, what's happening in the logic gates is what they call a transistor, which is if it's off, the signal doesn't go through, and if it's on, the signal does go through. So this is again your 1s and 0s. If the transistor's off, it doesn't matter what the data is. Nothing's going through. If the transistor's on, if the data's 0, 0 goes through. If the data's 1, 1 goes through. Now, the 1 goes through based on the Hall effect. And what the Hall effect is that even though you have a barrier where electrons can't pass, if above that barrier you have a voltage field, then through quantum physics, the electron passes through what it shouldn't pass through. It jumps to the other side. So again, they've been using that that has been in use since the 60s.
How is it that we can use things we don't understand, John? Or is it just that I don't understand it?
Well, and it's part of this 5-year thing that this is going to happen. Is there are things we don't understand, but people, engineers, if you will, and programmers do the same thing in logic. They know the goal they want to achieve, and then they muck with things. And then they see how that works. So the whole thing with the transistor was they were mucking with things. Oh, well, okay, let's go to the vacuum tube, right? The vacuum tubes were the transistors before transistors. Vacuum tubes are the analog version of transistors. So you have a vacuum and you have a coil, and if the coil is hot, then as an input comes into the vacuum tube on one side, it picks up the hot field, the hot glowy field of the vacuum, and in the vacuum, it transfers that energy with increased voltage, if you will, increased signal. A vacuum tube increases the signal. Right? So you're playing the guitar and the microphone is picking up a signal. The microphone sends it to the vacuum tube lead. Uh, inside the vacuum tube, a second lead powers the filament. The filament energizes the vacuum, and then the sink. So the sound comes in, the signal comes into one side of the vacuum tube lead. The energy of the filament is transferred to the signal, and a amplified signal comes out the other end. So that's how a vacuum tube works, but it works in analog, and that's why your audio snobs will will do vacuum tube equipment, because they get a pure analog signal. Transistor does the same thing in digital, but you only get ones and zeros, and there's a threshold. So an analog signal comes into a transistor. If it's too low, 0 comes out, even though it's 0.3 or something like that. If it's above 0.5, and it could be way above, it comes out as 1. That's how your transistors work. You just get zeros and ones.
So it's like a probability, or it's like a sorting mechanism almost.
It's very similar to a sorting mechanism, or in an audio term, you'd have a high pass filter or low pass filter, right? Because you have that. Anyway. So your transistors now, that's where the clipping comes in the audio, right? It pops in clipping, because the transistor had to turn it to a 0 or a 1, and if it jumps abruptly, you get a pop or a click, or you lose the audio, because it was too weak to pass the ones and zeros.
So as that technology evolves, it gets better. So there's less popping and clicking, and that's why songs get like remastered with new technology.
Yeah, they get quote unquote remastered, because in the old sense, it's analog media, but in general, what's happening is sophisticated algorithms are what are quote unquote remastering it or colorizing it, and then we leap to AI, where AI now colorizes it or remasters it, because algorithmically they're just saying, oh, if you see a pop, recognizes a pop, and here's how you smooth it out. Or if you see black and white and they wore brown suits in the day, depending on the color of square of gray, make it this brown. And then in the algorithm sense, you can have artistic license of all the ties should be red and all the dresses should be blue, those kinds of things. When you go to AI, then AI is pattern matching. So you just say, here's a movie I liked that's in color. Here's a movie that's black and white. Colorize the black and white movie according to the movie I liked. So just follow the pattern. And then you get some unpredictable stuff. But let's get back to quantum mechanics. So we talked about the Heisenberg uncertainty problem, and measuring, and the point of you have all possibilities at the same time. We've talked about the Hall effect, where because the transistor is quote unquote on, electrons go through, kind of like the vacuum tube. And if the transistor's off, it doesn't matter what the electron is, it's not going through. Now let's get to what they call quantum entanglement. And quantum entanglement's significant in our day-to-day lives, because so mathematically the quantum algorithms work forward or backwards. So there's no sense of time. You can go backwards in time, you can go forwards in time. When you add entanglement, it's and this is theory, it's not, when you add entanglement, it gives a forward motion to time. And an example here is you have a glass of ice on your table next to you, right? What makes the and you have room temperature, which is above the melting point of ice. What makes the ice melt? And you can talk about Brownian motion. Brownian motion is where molecules crash into each other and they transfer temperature, right? So a high temperature, high vibrational molecule crashes into the water molecule that's frozen and it transfers some heat, right? But you can also talk about quantum entanglement. Now, the point of quantum entanglement is when two particles become entangled, they operate the same way. So they don't have to crash into each other. When an electron in a molecule of ice gets entangled with an electron in a molecule of oxygen, all of a sudden those two molecules have to vibrate the same because they're quote unquote entangled, which would change the temperature of that molecule of ice. So over time, through entanglement, the ice can melt and it's not going to go backwards. That's where you get a forward motion of time. Okay, so let's go back to quantum networking, which is well ahead of quantum computing. So you have a wire between 2 points. Now, if you can entangle an electron, so now you have 2 electrons, right? And they're entangled. And you move one electron down the wire and preserves its entanglement, right? Now, in electricity in copper travels at 1/3 the speed of light.
When you say preserves its entanglement, does that mean that it could become disentangled?
Yes.
Okay, cool. Can you just
Yeah,
keep
and
going?
you would
I just wanted to make sure I understood.
You treat that as a loss, right? I'm going to send 10 down the wire and 8 make it. Okay, that's fine, right?
Yeah.
Because I'm going to send 10 more and 8 more make it, and now I've got my 10 that I needed, and the rest I throw away. So it travels down the wire at 1/3 the speed of light. Okay, but now that it's entangled, I can read the entanglement, and now it's happening instantaneously.
But why is it happening instantaneously?
Because the electrons are entangled. So because the 2 electrons are entangled, if I push one and turn it to 0, the other one turns to 0. If I push one and turn it to 1, the other one at the other end turns to 1. They are entangled. And they have to operate in all physics characteristics exactly the same.
Oh, wow. And because you pushed it down the line in time,
I physically transferred it.
Okay.
In its entangled state. So I had 2, they were entangled close together.
Yep.
I moved the one to the other end. If it remained entangled, all of a sudden communication is instantaneous. I'm not penalized by the 1/3 speed of light. Now let's go to Wall Street, right? So Wall Street firms bought up real estate as close to the
We're going all over the place in this one.
Yeah, but I mean, here's a physical problem, right?
Yeah.
So Wall Street firms got as close to the New York stock market as they could because that 1/3 speed of light meant that they got the trade before somebody a block away got the trade.
And that's why that area is expensive to live.
Right. But if you have quantum entangled networking, I could be in LA and I could send the buy signal to New York Stock Exchange instantaneously. And I could receive the New York Stock Exchange price changes instantaneously. That's quantum computing in the network sense, not in the Heisenberg uncertainty principle sense. And you can see how concrete that is.
Sure.
Right? It still takes me, half a second to move an entangled bit to New York Stock Exchange from New York.
Yeah.
On a good day, right?
Yeah.
But for what I need it, once it's there, for what I need it to do, it's instantaneous, and I don't have the physical problem of latency.
So
I have
okay,
zero latency, I
I see.
guess is the point.
I think I see where this is going. I think I see where this is going. You keep going though, because I don't want to say it and sound like a crazy person. I'll
No,
say it on I'll say it on a
I think I
phone
painted
call.
the picture. Yeah, I painted the picture. Quantum networking is it's happening right now.